Welcome back for another episode of Electricity with Grandpa. Actually, I have a number of great grandchildren. I don't know if I have any great, haven't heard lately. But anyway, one thing I wanted to, whoever's watching these videos, and I hope you're enjoying and learning. And if they're too slow for you, well, then watch something else. Because I paste these to give people time to think who are hearing some of this for the first time. The rest of you, if you already know a lot about this subject, this is not a good review for you. As you probably figured out, I am a Marine Vietnam veteran. I'm a Jeep guy. I'm into Jeeps. I've been into many things throughout my life. I've just really been blessed. One of the things that I wanted you to consider, those of you that are watching these videos, is we're all sitting in history, we're on this side of all these discoveries. So remember in the very first video we mentioned Thales, a Greek person who was rubbing some amber with a piece of wool and discovered static electricity. And of course, he wasn't the only one to discover it, but he got credit for it. Nonetheless, imagine yourself in that position. You weren't just walking along and you had a piece of amber and then you saw a piece of wool and said, well, I wonder what will happen if I rub wool on this piece of amber. No, he discovered it by accident. So almost everything that we're showing you in terms of technology, in terms of phenomena, like with creating electricity chemically, I think I told you that back even before the acid storage batteries, someone discovered if they took two metals, wires, two different metals like iron and constantan, twist them together and put them in a jar of whale oil and heated it up, it produced electricity at the other end of those two wires. Well, they just weren't walking along one day and thought, hey, I wonder what will happen if I do this and this and this and that. No, these ideas had to come from someplace. They weren't in these people. So I want you to ask yourself, where do you think these ideas came from? What inspired somebody to try something? Because they weren't born with it. Nobody is born with any knowledge. You have to acquire it from other sources. So where do you think they got these ideas? Where would the first person that made a discovery of something have gotten that idea? He couldn't have gotten it from someone else. And he wasn't born with it, so where did it come from? Just a question for you to ponder. We're going to get into this next episode with force and motion, and we're going to use plumbing and water and gravity to develop our discussion of force, resistance, and flow, or movement, force and motion. So let's jump into this, and we will not finish it in this episode. We will continue this with more elaboration on the relationship between force, the opposition to the force, and the flow that results, dependent on how much force and how much resistance you have. So let's jump right in here and do this.
Force and motion. Some years ago, I coined a phrase, you can make a motion, but you have to force the flow. So this had more to do with marketing for wind energy and solar energy. It really had nothing to do with basic electricity magnetism. However, if you think back into part one, you could take a magnet and move the magnetic field through a conductor, and the magnetic field produced by the electrons in the magnet put the electrons in the conductor in motion, but then they immediately stopped. If you want flow, you have to force it. You have to have a continual pressure, and you have to have some sort of force to keep something flowing. So you can make a motion, but you have to force the flow. So this is the topic, is actually talking about force and motion. One of the pleasures of lecturing is finding real world examples or examples from everyday life, or finding illustrations that people can identify with to explain electricity and magnetism. So you're probably wondering, what does this photograph of a old western town and a water tower have to do with force and motion? Well, you have two water tanks there. Maybe you didn't notice the second one, but halfway down the tower or so, there's another tank. So when you look at these two tanks, let's say they're both full of water. If you were going, and let's say you had separate pipes coming down from each tank with a valve and a shower head, and you were going to stand underneath there and take a shower, which tank do you think would provide the most water pressure? Now, you would probably say, well, the highest one. Well, put in scientific terms, it would be the one that has the greatest potential. So the upper tower has a higher potential than the lower tower. Now, potential energy. So it took more energy to get the water up to the higher tank, so you get more energy through the water when you release the water to come back down. So if you look and relate this to voltage, the upper tower has a higher electrical charge than the lower tower, but it took more energy to force more electrons away from their atoms to create the greater charge. So the higher tower represents a higher voltage, but it took more work. So you don't get anything for free. There's an old saying, there's no such thing as a free lunch. And the laws of thermodynamics, one of them says, you can't win, you can't even break even. So there's laws of efficiency. So anyone who proposes a free energy system is deluding themselves. It always takes more energy to produce the form of energy that you want than what you're going to get out of it. So if you want to put it in kilowatts, it's going to take more watts. If you want to take something like water power and generate electricity, the electricity, usable electricity that you're going to get will be less than the water energy that you use coming down through gravity. However, that doesn't mean that the system's bad. That's just a fact of life, that anytime you convert energy from one form to another, you lose something. But these systems still work very good. Another illustration that could be made from these two tanks would be stretching a rubber band. If you were to anchor a very large, long rubber band at the bottom of that tower, and we'll say the rubber band was 4 foot long, meaning it's 8 foot of rubber in a loop, okay? And so you anchor at the bottom of the tower and you stretch it up to the top of the middle tank. It's going to take a certain amount of energy to do that. But to stretch the rubber band all the way up to the top of the higher tank is going to take a lot more force and a lot more energy. Consequently, if you stretch the rubber band to the top of the middle tank, the lower one, when you release it, you get a little snap. And if you stretch it all the way up to the top of the higher tank and release it, you're going to get a big snap. So if you just look at potential energy in terms of stretching a rubber band, the further you stretch it, the more energy it's going to take to stretch it, but the more energy you're going to get when you release it. Just like shooting a rubber band, you hook it over one of your fingers, pull it back. The further you pull it back, the further it's going to travel when you release it. Well, as long as we're looking at water towers, why not just continue on with that example? Actually, I created these graphics first, then I found the picture of the water tower. In other words, I was looking for a real water tower, and I happened to see the one in that old western town and thought that was more interesting. So here is your public utility for water. Somewhere there's a pumping station, whether it's pumping it out of a well in the ground, out of an aquifer. Aquifer, that just means groundwater, or actually it's a pool of water in the ground. It could be an underground river as well. In Michigan, in western Michigan, where I spent quite a bit of my life, they actually pump the water out of Lake Michigan, and there's a pumping station halfway between Lake Michigan and Grand Rapids, which is about a 35-40 mile distance. So water is pumped out of some large endless reservoir of water, underground or a lake, and it's pumped into a tank. This is the charging system. So we're going to charge our system with a pump, an electrical pump that will have some controls on it, and we want to keep this tank as full as possible. The tank itself is storage. If there's no water in that tank, there is no force of gravity on the water that's felt down through the pipe. If we open a valve in the house, we have flows. So water flows out of storage through the residence, through the drain into the soil. It could be a septic tank, or it could actually go to a waste treatment facility. We'll just say it goes into the soil in a septic tank. And if you know anything about septic tanks, the solids settle to the bottom, and then the water leaches out into the soil. And as it travels down through the soil, it's filtered and cleaned and purified, and then it goes back into the aquifer, or somehow it gets back to the source. How much flow that you have, if you think about this, you've got, let's say that's 10,000 gallons up there. If you opened the valve, why wouldn't all 10,000 gallons come down instantly? Well, you realize that's absurd, but we're just making a point here. Why wouldn't all of that water come down in an instance? That's because flow is limited by resistance. So pushing back against the force is the size of the pipes, the valve changes in direction as the water flows down and goes back to the soil. Now I realize that inside your residence you have bathtubs, showers, sinks, ice makers in your refrigerator. All of these are points of resistance that are controlled to control the flow. But even if you opened up that pipe right where it enters the house, wide open, the flow would still be limited by the resistance of the size of that pipe, the friction on the inside of the pipe. Looking at our system in very light mathematical terms of ratio and proportion, and I want to further elaborate that pipe that comes down from a storage tank to your house, another way for you to look at how the size of that pipe, in other words, the inside diameter of the pipe, affects the flow, is if you compare it to a straw. I'm sure at some point in your life you have had something thick to drink out of a glass, out of a, some vessel, and you put a straw in there, and the straw was kind of skinny, or, very small inside diameter, and you had to suck really hard, to get what you wanted up out of that glass. If you had a larger straw, you still had to apply a fair amount of force, in other words, suction, but you got less resistance from the actual straw. You still have some resistance from the weight of what you're pulling up through the straw, but the larger the straw, the less resistance you have from the straw itself. So I think this is a very easy to understand illustration. So if we put force, flow, and resistance in another form, we would say that flow is equal to force divided by resistance. So let's just stop and look at this a minute. I think that probably most people that are watching this video understand basic ratio and proportion, or fractions. So here we have force over resistance. If the force increases, the flow increases. If the resistance increases, then the flow decreases. So in mathematical language, we would say that force and flow are directly proportional. More force, more flow. But then we would say that flow and resistance are inversely proportional. The more resistance, the less the flow. So force and resistance are inversely proportional to flow. That's why they're placed with force above the line and resistance below the line. So I think this is very easy to understand. And when we actually, if we were to get to so far as to quantify electricity, this would read current flow equals voltage force divided by electrical resistance. So the greater the voltage, the greater the flow of electrons. The greater the resistance, the lower the flow of electrons. And if you want to relate that back to the earlier parts of this presentation, remember that copper has one valence electron, one free electron, and copper is a very good conductor. However, silver is better than copper, and that is because the heavier materials, although they still only have one electron in the outer orbit, that outer orbit is further away from the nucleus than it was in the copper atom, which means silver has less resistance to electron flow than copper. For right now, we'll just keep it in those simple terms. Now, how would you compare that to the pipes? We'll say a copper electrical conductor would be analogous to a 1-inch inside diameter pipe, silver a 2-inch inside diameter pipe. And think of the mathematics involved here in these very simple terms: directly proportional, inversely proportional. Well, let's quantify our public utility freshwater system here. If we want to quantify the amount of force, we're going to do that in terms of head, and we'll do it in feet. So head pressure is the height of the top of the water column above the point where you're going to use it. And that includes the water in the tank too. Now, if this tank were twice as large in diameter, but the water level still was no higher than what you see here, the head pressure would remain the same, even though you're thinking, well, there's more water up there. This is done with a vertical column. So if you take and travel straight up the pipe, and when you get to the bottom of the tank, you keep going straight up to the water level, that's what you're measuring. You're measuring the amount of weight straight down through that pipe, and that's measured in head. You can also relate it to pounds per square inch. And what we're talking about is gravity, right? Atmospheric pressure, gravity pressure. If we take that same tank, and in a case where there's high water usage in your neighborhood and the pumping station can't keep up with the usage, and that's not uncommon. However, the pumping station takes into account that that tank can get almost down to empty. As long as it can keep it from going empty, everybody has some water. But the water pressure does reduce because the head, or the height of the water, the top of the water column, is now lower, so you have less pressure. This would be very easy to compare to a battery. When a battery is fully charged, that's like a full storage tank. As the battery discharges, like when you're starting your car on a cold winter morning and it's just cranking away, and pretty soon you start to hear it a little slower, that would be the tank over on the right. What you had stored up in your storage battery is now being depleted. Now, although that battery can recover chemically, you're still going to need to get the car started to run electrons back in the negative side of the terminal to build the charge back up. This is a very good comparison of the voltage dropping when there's a high demand. So almost in any household, you have at least one device that when you turn it on, the lights dim. In other words, you might be sitting there and then all of a sudden you see the lights kind of flicker. That could be because an air compressor kicked on in the garage, or the sump pump kicked on down the basement. Usually most appliances don't have that much instantaneous drain, but it's all comparable to what we're talking about right here. Here we have two different residential public utility freshwater systems. And considering what we've talked about so far, I think the first thing you would notice is the one on the right has a higher tank than the one on the left. Therefore, the one on the right will provide a higher pressure, higher water pressure than the one on the left. Now, in my place down in the Dominican Republic, all homes down there, if they have what you would call running water, it's from a tank on the roof. So we have an on-again, off-again public water utility that sends water at different times of the day up into our neighborhood into a pipe. And we have a reservoir, a cistern, underground. And so that public water flows into that cistern. And when we have public power, because the power goes off every day, we have a electrically powered pump that pumps water from the cistern underground to a tank up on the roof of the house. And we have a float switch inside of that tank that turns the pump on if the water level drops. So usually what happens, the power goes out every day and you keep using the water. The instant the power comes back on, the pump kicks on, it pumps water up there. The point I was going to make was that my bedrooms and office are on the second story. So the water tank is about 4 feet over my head when I'm taking a shower, and the water travels a very circuitous route to get to the shower head. It actually goes down and back up to the shower head through the hot water heater. So the water just basically dribbles out. But downstairs on the first floor, they get reasonable water pressure. I'm not complaining, but if you wanted to, you could say that this represents a low voltage system and a high voltage system. So the one on the left would be, say, 24 volts DC, and the one on the right would be 48 volts DC. It takes more energy to charge the higher system, but you get more energy out of it. You have more force through relatively the same amount of resistance. Now, you could argue that there's more pipe going down the downcomer down to the house on the right than there is on the left. So there's a little bit more resistance over on the right, but believe me, you're going to get a lot more pressure from the system on the right than the one on the left. Okay, we've upgraded our public utility for fresh water to include your neighbors. And you're on a little dead-end street. Now we know there's going to be more than 4 residences on a water tower. But this is good for our illustration. Looking at this picture, if you were going to define the difference between residence A, B, C, and D, since A, B, C, and D as far as a house is concerned is identical, its sewer pipe or waste lines are identical. The only difference between the 4 is the downcomer, or the plumbing coming from the water tower down to the houses. Now there's really only one large pipe coming down from the water tower, but to keep the diagram simple, I did something a little bit different, but the illustration is still good. House A and B are being fed directly from a pipe, but house A has a longer pipe with 2 elbows in it. Houses C and D, not only do they have an elbow or 2, but both homes have to draw their water through the same pipe. So the resistance of that initial pipe is affecting the flow to both residence C and D. So that having been said, which home here, which residence, A, B, C, or D, would have the greatest flow of water? And remember, all 4 of the homes have the exact same pressure. When there's no water flowing through the pipes, and you were to measure PSI or pressure at the entrance to each home, the pressures would all be equal. So you're thinking, well, why would the flow be different? Well, we'll see. Which residence will have the highest available flow? B. B has the least resistance. Now remember, when there was no flow, the weight of the water in the vertical column was the same because it's based on the height from the point of entry up to the water level in the reservoir, the tank, the storage unit. But once the water starts to flow, the pressure, some of it is dissipated in friction against the sides of the pipe. Which residence would have the lowest available flow with this given system? Well, A would be a little less than B simply because it's got a longer distance to travel through the pipe, and it's got 2 direction changes, and these direction changes produce heat from friction as the water travels with more pressure against the outside of the turn. Now that's small, but it's still there. Residence C and D, they share one common pipe coming out of the reservoir, so that means C and D are definitely going to be lower than A and B. Even though C is the same as A concerning pipe and distance, because it has to share the flow from one common downcomer with D, that puts C less than A. So which one would have the lowest available flow? Well, D. Not only does D have to share a downcomer, but it has a greater length of pipe to travel than A, and it has two elbows in it, just like A does, but it's a longer distance, plus it has to share the downcomer. Okay, what determines how much water flows through one of these residences? Now, this is not a trick question, but you've already been given the answer. Flow equals force divided by resistance. So when we compare these four residences, we compared the resistance. The force is equal, but the resistance is greater in D. C is greater than A and B, A is greater than B, and B is the least. B has the least resistance to flow for the same force, so it's going to have more flow. Okay, so how could we control the force? All of these families are paying the same rate to the public utility for water usage. However, the folks in House D happened to visit the folks in House B, and they noticed when they went in to wash their hands before dinner that they had a lot more water flowing, a lot more water pressure and more flow out of their faucet. And they thought, well, maybe they've got better faucets or better plumbing. And a couple days later, the husband's out in the backyard at House D, and he's got a hose hooked up to a spigot, and he's, spraying something, and his neighbor's got the exact same length of hose. They happened to be together when they bought them at the local hardware store, and he can't get his water to shoot out as far as the other guys. So, he starts checking, and pretty soon he realizes he does not have as much water pressure as the family in A and B. So, since they're all paying the same dollar, the power company had to do something to equalize the pressure. And so they came up with this device. It's called a pressure regulator. Now, I realize that this is not electrical, but it is demonstrating the balance of force to control the force.
Well, I hope that you learned something from this presentation. I actually made this quite some time ago, and I re-edited it to try to trim it down a little bit and to make it more interesting. We ended with introducing the idea of a regulator, and that is a mechanical regulator that opposes gravity with a spring. And we will pick this back up in another episode. So if you were to back up into that video, the last image was a pressure regulator that had a spring with an adjustment, and you adjust the spring to oppose the pressure coming in from the tower to maintain a constant pressure on the house side. Now, if the pressure from the tower drops below the setting, then the pressure in the house is going to drop too. So a regulator only works as long as the force you're regulating is greater than the set point that you set it to. We'll leave it here, and we'll pick it up in another episode. Thank you for watching.